Time to talk about some electron configurations that are a little unusual. If you've looked at this chart from the text that shows all of the valence shell electron configurations, we'll notice that typically they progress such that one atom has one more electron than the previous atom. But there are some places which have some unusual characteristics. So let's look at the first row of the transition elements. Scandium 4s2 3d1, titanium 4s2 3d2, vanadium goes up to 3d3. Wait a minute, here comes chromium. What? 4s1 3d5. There's an anomaly. The next element will have 4s2 3d5. It's got one more electron, manganese does, but the pattern between vanadium and chromium is a little odd. We're not adding just one to the last subshell. Another anomaly occurs over at the end of this first row. So if you go from iron with 3d6 and cobalt 3d7, nickel 3d8, whoops, all of a sudden here's copper that has a different pattern than might be expected. It doesn't have 4s2, but it also doesn't have only one more d electron than the previous element. How do we understand this? Again, these are only the valence electrons that we're looking at because the inner electrons, everything except that outer shell, everything inside the outer shell is all going to be the same for each of these elements all the way across this first row of the transition elements, as is the ones preceding it, calcium and potassium. So what's with the valence electrons? Well, the expected configuration we would have imagined would have had 4 d electrons for chromium and 4s2, and for copper we would have expected 4s2 and 3d9. In other words, just one more in the d shell for each of those than the element that precedes them. Double check. Look again, chromium and copper. So we were expecting chromium to have 3d4 because the preceding one was 3d3, and then nickel 3d8 and copper we expected to be 3d9. It's not. So what's happening here is there is evidence for the fact that there are certain configurations that are more stable than you would have otherwise imagined. There's experimental evidence to support this, which we won't discuss for now, but the actual configurations verify or demonstrate the possibility that filled or half-filled 3D subshells are more stable instead of having a full 4s subshell. In other words, if you take the two choices for what we see for chromium, you have 2 half-filled shells in the actual configuration instead of 1 full and 1 partially full. So the preferred or the more stable arrangement turns out to be 2 half-filled subshells, both the 4s1 and the 3d5. And then for copper, instead of having 3d9, which is all but full, you end up with a half-filled 4s and a full 3d10. So half-filled applies to chromium and the full applies to copper. But in each of these cases, we have configurations that are verified by physical evidence that suggests that something other than just one more electron is the actual occurrence. So the fact that these inner shell electrons fill up or half fill a 3D subshell instead of filling up the 4s shell is not necessarily obvious to us. We call that anomalous electron configuration. There are other interesting anomalies that we won't go into great detail to explain, but we can take a note to recognize that there are others. So if we go back to that chart, so chromium was and copper were the two we began with. If we look at the neighboring elements in their groups, there are some other anomalies there too. So molybdenum below chromium has an analogous pattern with an S1 and 4D5, but look at its neighbor. Niobium also has something funny going on there, which we wouldn't have expected, nor will we explain. And then the elements underneath copper, such as silver, which has a 4s1 4d10, and gold has 6s1 5d10 with F electrons in between. Those are analogous to the pattern for copper. but there's some interesting things going on in platinum, just there adjacent to gold. If we continue the pattern underneath chromium and molybdenum and look at the row with tungsten and tantalum, well, guess what? Not exactly predictable and not exactly for us to concern ourselves. So these patterns are anomalies, but the only ones, oh, there's another one, sorry. Ruthenium and rhenium and palladium. Wow, those are interesting. No, we will not explain those. So don't expect that absolutely everything is as clear cut as we might first imagine. The two that you need to pay attention to are chromium and copper. Know that they're unusual, and we'll talk about some of their what the consequences of those anomalies are with time. So beware that you're going to notice what the proper and actual configurations are for those two elements, including filled or half-filled 3D subshells rather than having a full 4S subshell.